Okay, this is chapter 9, the last chapter in soil dynamics course at BiT with a live recording. This is introduction to ground response analysis and soil structure interaction analysis. So this is more of introduction for the two sections because this is very practical, especially in computer modeling. So we'll see section 9.1 for the introduction to ground response analysis, also known as site response analysis. So if you see it, whether it's a ground response analysis or site response analysis, it's the same thing. And then we'll see section 9.2, introduction to soil structure interaction, SSI analysis. So in the previous 8 chapters, we have seen how earthquakes originate from the fault, how they travel, and soil dynamic properties, theory of vibration. And now we're going to see how we do ground response analysis, especially after the waves arrive to the bedrock. That's usually seismologists doing that from identifying faults and prediction of how the waves pass, and then from the bedrock to a nearby soil and to the site. That's more of a geotechnical engineer and structural engineers dealing with that. So if we are doing the analysis without the structure, that's ground response analysis. If you remove this structure, apply input and propagate that input to the surface, that's called ground response analysis. We need the soil properties. That's why we saw the dynamic properties of the soil, and we can perform linear analysis, equivalent linear analysis, or nonlinear analysis using different softwares. And there are software capable of doing this SSI together with the soil and structure. And they can model. The soil is usually too big to model for many softwares because you have to, in some cases, you have to go way deeper. So, but there are some approximations like using the wave propagation theory for the soil and finite element for the structure in combination. So software like SSI, that's what it does. FLAG has also a capability to do that, but it's more advanced in the geotechnical portion, very limited for the structure. And also it has limitation how much soil it can model, because FLAG considers finite difference for the soil portion. The more finite different elements you have, the more time consuming it is. So a few terms for ground response analysis. We know what bedrock is. Usually we have our input at bedrock. Even our recording station can have a bedrock, or seismologists can produce, input at the bedrock level. And free surface motion is the one which doesn't have the influence of the structure. If you don't have the structure nearby, then free surface motion is what you get. Or you can have also outcrop, where the rock is going up to the surface. So rock outcrop motion. In some cases, you may not have soil, so it's bedrock outcrop, no soil in it, and rock outcrop motion at the ground level. So in terms of analysis, site response analysis can be performed using linear properties, where you have the G, the Vs, the shear wave velocity, and the damping, which are constant, like a static analysis. Or we can use equivalent linear analysis piece by piece. Those dynamic parameters, they change with the strain. So depending on the strain level, softwares pick the corresponding shear modulus, damping, and shear wave velocity. Or there is a nonlinear soil properties, like when we have constitutive models to model very reasonably the hysteresis loop, like a field model in FLAG. This one is usually done in time domain, more time consuming. Equivalent linear, usually it's like in Shake and SSI, it's done in frequency domain, it's much faster. Because in frequency domain, you select your frequencies. We don't do it at any continuous frequency, just selected frequencies. We know which frequencies are very important, something like a fundamental mode of vibration. If you have a soil, then you know which frequencies are very critical. There may be 5 or 10, but conservatively you can model 20, 30, or 100 frequencies. You solve for those frequencies and you combine the result. So it makes it faster. But in time domain analysis, you go with increments, very small time step, 10 raised minus 6, something like that. So that's why it takes a lot of time. So today, site response analysis can be performed in two ways. From solution of wave propagation equation, so they solve directly the wave propagation equation, like Shake software, Deep Soil, and SSI. Or they use using numerical method to model soil using finite element or finite difference method, Fluxery 3D, Plaxis, etc. And it's done usually in time domain. So transfer functions, this is the simplest analysis you can do using transfer function. Transfer function is when you have the dynamic properties constant and the input motion at the bedrock, use you transfer multiplied with transfer function, you have some kind of function developed for the structure or for the soil, and it directly give you the output motion. Because the parameters are constant, you just do it in one shot. So main assumption is that dynamic properties, shear wave velocities, P wave velocities, shear modulus, and damping, they remain constant with the strain. So the entire soil is represented by transfer function. We'll see those functions shortly. Just to give you an example, let's say you have a ground motion at the bedrock level, and this is in frequency domain, and you have that fast Fourier amplitude spectra. So if you have a time history, first we have to convert it into phase in frequency domain. That's how this transfer function works. Then we multiply it by the transfer function, and we get the output at the surface. Very simple. Change your time history into a phase. There are softwares doing that. Develop your transfer function, type, multiply it, and get the structure response at the either on the structure or at the ground surface. Or you can go backward. If you have the input at the ground surface, you can divide it by the transfer function and get the motion at the bedrock or whatever depth it is. So this is the simplest. Let's quickly recap what we studied in chapter 3, solution to wave equations. So one-dimensional wave equation, you remember like in one direction, let's say this is in the Z and U. So you can have this partial differential equation. The variation, the motion or the displacement with respect to the time and the depth. So this V can be VP or VS, shear wave velocity, P wave velocity. Even it can be, if it's on the surface, it can be Rayleigh waves and lava waves. Note that at specific time and depth, the wave equation provides a solution to two waves, incident and reflected wave. We have seen this. So you can have two waves from the solution of this equation. So the displacement at any depth and time can be given by these two forms. And there are two waves. One is going down and the other one is going up. So this is just a recap. We have seen the detail in chapter 3. You can go back and look at it there also. Now let's develop the transfer function of soil and for different cases. And this is directly from the wave equations. Case 1, let's assume homogeneous and damped. So there is no damping. In the simplest case, assume there is no damping. And rigid bedrock. If you have a wave on rigid bedrock, what happens? Is it a good idea to have a rigid bedrock for a wave propagation problem? Helen, is it a good idea? If you have a wave comes down here, what happens when it comes here? This is rigid. If it's rigid, then it's going back, right? So, but in our simplest case, let's assume rigid case, the rock doesn't have any damping and the wave is reflecting back and forth. So you expect some kind of energy trapped. So let's forget that for now. Let's assume in simple case, no damping even in the soil, no damping in the rock because it's rigid. For that case, the displacement of the wave at any depth, Z, from the surface to any time t, at any time t, we know that this is a solution from the wave equation. A and B are parameters. Omega is the forcing frequency, K is the wave number, Z is the depth. So we can use these parameters and get the A and B and the unknowns. Constants A and B can be obtained from boundary conditions. We have boundary conditions, the ground surface, we have the rigid surface here. Shear stress at the ground level is what? It's zero, right? It's a free surface. So it's zero. You can solve this. So Z is equal to zero is the ground surface because our coordinate is at the surface. So shear stress is shear modulus times shear strain. Get a derivative of that and solve it. So if you differentiate this, finally you will get this equation. Shear modulus I is a complex number. K times A minus B exponent I omega t. For this number to be zero, we should have A and A equals to B. The others cannot be zero. So A must be equals to B. So if you solve it, then we get the displacement at any depth, at any time t, it's given by this. So if you have a wave, then its displacement can be given by this. This is assuming just no damping. We'll get to it. We'll see a case where there is damping and when the rock is not rigid. We're just approaching it from the simplest and going to the more complex one. The transfer function between any 2 points in the soil can be obtained as follows. Assume surface and bedrock for the 2 points. So let's say you have 2 points, one at the bedrock, one at the surface. The transfer function is ground surface motion, this one, bedrock motion. Or in this case, we're going down. Since we're going down, Z is at the top, 1 is here, 2 is here. So ground surface motion at the top, and 2 is the bedrock motion. So this is the ratio. The displacement at 0Z and at H. H is the thickness. So we are getting the displacements at the ground surface when Z is 0, and then at the bedrock. You can find this at any depth. If you do that, we know this, the displacement is this, and you can find the ratio. Transfer function is what? Is the ratio of between 2 points. Because our goal is to get we usually have the ground motion. If we know the transfer function, ground motion times transfer function will give us the ground surface motion. It's the simplest we can do in linear analysis. So that transfer function F1 in terms of omega and frequency domain, it comes out to be 1 over cosine of omega H by Vs. H is the thickness of the soil. Vs is the shear wave velocity. So this is a simple equation. So absolute value of the transfer function is amplification function. So all you need is trying to get how much it's amplified usually from the bedrock to the surface. Or if you have it here, then getting the bedrock. So this is our transfer function for the simplest case, no damping and rigid bedrock. And look at it, all are known. Omega is the forcing frequency from the motion, we note. H, we note, which is the thickness of the soil. Vs, we note. Vs either from field test or from lab test, shear wave velocity. So if we know the transfer function, then, which means if somebody give me the motion at the top, at the ground surface, or at the bedrock, I can easily find that, the other point. As KH or omega H Vs approaches, if you see this transfer function, you can plot it. See how it looks like. F1 omega in terms of power 2, 3 power 2, and you see these peaks. What are these peaks? So at every pi by 2 plus n pi, you see the peaks. What are these peaks? Yusuf? This is where the motion is going to try to be infinity. Look at it. As these values at these points, the denominator approaches zero, right? The cosine value approaches to be zero. If the denominator is zero, 1 over 0 is how much? Infinity. Is that realistic? No, it's not. This happened because we're not considering. These are resonance points. So we are having so many resonant points, so many modes. We know that in theory of vibration, we looked at least one point we had at that point, right? But for soil, look at it. And for soil and structures, you'll have so many resonance points where the amplitude tries to be infinity. The resonant strong motion of the soil depend on the frequency of base motion, depths, and wave velocity, right? These parameters. The first resonance occurs at, this is the first resonance. It occurs at omega h by Vs equal to pi by 2. And if you solve this, the fundamental, we call it the first one, we usually call it fundamental frequency or fundamental period or natural period. And usually it's the dominant one, right? But in this case, almost all of them are dominant. You'll see next how the others are not dominant. But here is the thing. For our soil case, the transfer function is giving us the first mode of vibration, the first natural frequency. It occurs at 4h by Vs. Who remember this equation? Yeah. You remember it when I talk about the 1985 Mexico City earthquake, the resonance? I use this equation, right? When I come up with a 2-second fundamental period for the soil deposit, I told you at that time, don't worry about this equation. But this is how we determine the fundamental period for soil. So if somebody asks you what's the fundamental frequency of your soil, frequency, you can use the reverse, Vs by 4h, period is 4h by Vs. But now we are having so many peaks, so many resonance points. This is because we have a big assumption at the get-go. That was no damping case. When we introduce damping, something will happen. You'll see it. So case 2, homogeneous damped soil on rigid bedrock. Now we are improving it a little bit. We are saying our soil now has damping. In the first case, we didn't have damping in the soil. Now we introduce damping. But still, we are assuming constant parameters. That's how transfer function works. So for solids or soils whose resistance to shear deformation is the sum of elastic part, viscous damping part, Kelvin-Vogt model status, the shear stress at any point, it has elastic part and it has the viscous part. We were using this previously, just linear assumption. Now when we introduce damping, viscous part, we're using the Kelvin-Vogt model for the soil. Now we are introducing damping into the motion. The corresponding 1D wave equation with viscous damping. Remember, this is the wave equation without damping. Elastic waves, we were saying. There was no damping. If you are introducing damping into the soil to be more realistic, now we have a third term, which includes the damping part. The damping comes in this coefficient, and that coefficient has a damping value, 2G by omega and damping of soil. So this is the same wave equation, but now we included damping. You can see the detail of this equation in the reference 1, chapter 5.15, section 5.5.1. That's the Kramer book. So the solution of this wave equation is the form. Now it's similar wave equation form, but the wave number now changes. It becomes K star now. Because it includes what? It includes damping now. It's getting more complex. Where K is a complex wave number with a real part K1 and imaginary part K2. The shear modulus that we were assuming constant, now it depends on damping. And it's a complex number, I and damping. Damped complex shear modulus. Same is true for if shear modulus is dependent on damping, then shear wave velocity is also the same. Shear wave velocity is square root of G by rho, right? So it's a function of damping, and it's a complex number now. A wave number is also it's omega by Vs star. It's dependent on the damping. So following similar procedure, like using the boundary conditions we used before, the transfer function now it becomes like this. So remember, before we had only this term for the transfer function when we solve it using the boundaries. We said shear stress at the surface is 0, and then we came up with this 1 over cosine kh. And it wasn't the square root because it's a square. But now we have a second term, sin squared, and the damping is coming into play. It's the same. You can follow, you can see the derivation in the Kramer book. But now the transfer function, it has a damping term. So same transfer function, the amplitude, you can get this. And you can see relations. Sin square y for any y, it gives you y squared for a small number y. If you can use that relation, this is just math. You can simplify this expression into just psi kh squared. So you'll have the transfer function simplified like this. Now let's see the graph of this transfer function. If you plot the amplification factor for this transfer function with respect to kh, then you'll get now, you have first mode, second mode, third mode, fourth, it continues. You'll have several modes, but see how the other modes are disappearing. Right? When we consider no damping case, they were equally higher, like they were trying to go to infinity. But no damping is unrealistic. Soil has damping, you know that. But when we are more realistic, you see how it changes? Only the first mode is significant. First mode also it went down because this was too large. I don't know how much we plotted before. We can go back and see it. Well, we didn't put number because this guy is going to infinity. But now it has limited value. This is 12 for this specific case. So you'll have a larger value of the first mode and some insignificant values for the other modes. If you remember, in our 1 degree of freedom analysis, I gave you an example where we said we get the first mode and we pick the acceleration there from the response spectrum and we multiplied it by 1.5, right? That 1.5 factor, what did we call it? MMF, right? What's MMF? Mamush? Huh? MMF, multi-mode factor. Multi-mode, because this is first mode, second mode, third mode, fourth mode, fifth mode, it continues like that. Structures are complex, soil is complex. They will have so much modes. But we get the value for the first mode, and the other modes are insignificant, they are small, but we increased it by 50% to account for the effect of the other modes. That was the reason. So do not expect you have only one mode. The first mode is the one dominant. You pick that acceleration in the pseudo-static analysis, but for the other modes, we say researchers, they found around 33% increase. but recommendation is to go up to 50% increase to account for the other modes. So now, the takeaway is when we consider damping, the first mode is the more significant one, and the higher modes they go down, especially for higher damping. You can see it. 5% damping is higher magnitude than 10%, than 20%. The 20% is getting flatter. The end's natural frequency of soil occurs, the ends, the first, the second, the fourth, at these values. And the fundamental frequency is omega pi Vs by 2h. And this value is occurring at a fundamental frequency Vs by 4h, or period is 4h by Vs. Same point, like with the no damping case. For multiple soil layer, weighted average Vs can be used. But in our soil now, we assume constant value, right? One value of G. But if you have so many layers, 2, 3, 4, 5 layers, Vs increasing downward, to estimate the fundamental period of the soil, you can use weighted average Vs value, because we have this equation like a single Vs value. It's okay to approximate it. So you can see it for n equals to 0, that's the first mode. This is normalized displacement plot with depths. N equals to 0, the first mode is the largest one giving you. It's like a cantilever deformation. Second mode, N1 and N2's more oscillation. This is like a beam. It's like considering a soil column and analyzing wave. It's kind of similar like a cantilever beam, even if it's not identical. Let's say an example. It's an easy example, but it may not be easy by hand because we have this input motion, but there are softwares to do this. But let me show you the concept. The size at which the Gilroy number to soil earthquake motion shown in figure 3.1, I already put that figure 3.1. This is from reference 1, the Kramer book. So if you see example 7.2, it has input motion, this. Gilroy number 1 bedrock motion. Was recorded is underlain by some 500 feet of soil, underlain by shale and serpentinite bedrock. This is a kind of bedrock, I don't know myself. The shear wave velocity of the soil varies from about 1,000 feet per second at depths less than about 130 feet to about 2,000 feet per second at greater depths. Assuming an average shear wave velocity of 1,500 feet per second square, an average unit weight of 125 pounds per foot cubed, a damping ratio of 5%, and a rigid bedrock. Compute the ground surface motion that would occur if the bedrock was subject to the east-west component of the Gilroy number 1 rock motion. So what it says is, this is using the linear analysis or using the transfer function. We already have the transfer function, right? This guy with damping. The damping is given, every component is given. So we know our equation. Now what we are given is bedrock motion. If we have the bedrock motion, if we know the transfer function, now the transfer function, what it is, I'm sorry, this is transfer function, TF. If we have the transfer function, what it is, it's representing the entire soil in a simplified equation. All the soil properties, if you put it in the transfer function, then it's representing the soil. So if you have a bedrock motion, multiply it with transfer function, then you will get it at the ground surface. Simple, right? But that transfer function is developed in frequency domain. Don't forget that. So we're not going to multiply directly the time history. This is in time domain. So we have to convert our motion into what? Before we do that? Frequency domain or the phase. Fourier amplitude spectrum, or we call it. So this is how it looks like. If you use some software to convert the time history motion into a phase, you have the bedrock motion. That's in time domain, right? Then change it into a phase, Fourier amplitude, Fourier acceleration spectra phase, bedrock motion. This is in frequency domain. Then what do? You multiply this, right? And you get, or well, you have a transfer function, F2. That's a plot of the transfer function. This is directly this equation, this. It's just plotted for that specific property of soil, because the soil properties at these values. So it's plotted, you see it. It's around 12 peak value and second mode, third mode, fourth mode, things like that. And these magnitudes, they change with the property of the soil. In this case, we are using these specific values, the damping value 5%, unit weight this, VS this. So this is how it looks like. If you have different depths of soil, it may increase or it may decrease. So for this specific case, plot it, or use some MathCAD, MATLAB, or even Excel can do this. Then now what do? Time history motion, you have phase in frequency domain, you have transfer function, then multiply these two, right? If you multiply these two, phase of ground surface, that's what you get. You multiply the bedrock motion by the transfer function, you get a ground surface, but it's still in phase form, frequency domain. So this is C times D. C times D will give you the ground surface. So the bedrock motion times the transfer function it gives you the ground surface motion. Simple. Now, if you want it in terms of time domain, you have to convert it from phase to a time domain. This is easy. It can easily be done. MATLAB has the capability, so many softwares. So now look, this is our result. Now we get the time history at the ground level. So this linear approach using transfer function is very simple, right? Very simple. Once you have your function, it's just multiplied. Note that 0.452 G, we get around 0.452 G amplified motion at the ground surface. Calculated is considerably greater than the peak acceleration of 0.322 G recorded at the glory number 2 soil. The glory number 2, what they did is they have a recording at the bedrock, they have a recording at the ground surface. So we use the one at the bedrock. We think without, we know the soil properties, we get the transfer function, we multiplied it, and we get the ground surface motion, right? But see the observation. The 0.452 G PGA we get using this method is much larger than the 0.322 G peak value, which was recorded during the earthquake. So our approach has something wrong, right? Anybody's guess? Whatever we estimated using the transfer function linear approach is much larger than what was recorded. It's conservative, but it's much larger than what's estimated. Why is that? Something must be wrong. Assume the soil is, we know the soil, the VS, the G, the damping is perfect. We had a good values, reasonable values from lab, but there is something else. Who can tell me that one? Fakado. So we said, so what we did is the giveaway number 1 earthquake, giveaway number 1 recorded at the bedrock, this is the one. We use our transfer function we just derived, and we get the output at the ground surface. That ground surface value is around 0.452 G PGA, this one. And this is much larger than what was recorded at the ground surface during the earthquake. So there is something wrong. Because at the ground surface, they get 0.322G, we get 0.45. That's like a 50% increase, right? So what happened? Assume the soil is perfect. The data from the soil investigation, the geotechnical engineers, they did a good job, so it's perfect. But there is something else. Factor of safety. Let me give you a hint. So there is a wave recorded here, right? When we transfer it to the ground surface, we consider damping for the soil, but we assumed rigid rock. So when seismic moves, what happens? It's back and forth, and so that this is because we're not considering rock flexibility, rigid rock. We're not considering damping for the rock. So the rock is not helping in anything. It's not absorbing anything. Basically, what we are having is like a trapped wave if you leave it there. So now we're going to improve it. So you will get much larger value at the top. Now we're going to improve it. We're going to consider some elasticity for the rock. In reality, even if rock is having less damping than soil, it can introduce some damping to help damp out, to absorb the seismic motion. So bedrock is assumed. That is the wave trapped. That's what I meant. So that's much larger than what is recorded. So basically the answer is our assumption in the analysis. Our assumption is still very conservative. We're not considering flexibility for the rock. Okay, that's where case 3 comes. Case 3 says homogeneous damped soil on elastic rock. Now, even if it's bedrock, it has some damping. We're going to consider some absorption by the rock. When the wave reflect and refract, the rock is also responsible absorbing the wave. So this is a more realistic approach. So very slowly we are getting a little bit complicated and getting also more realistic. Because the rigid assumption is bad. Initially, we assumed no damping in the soil. It's bad. And we improved it by introducing some damping in the soil. But we were considering a rigid rock. Now we said, okay, elastic rock. If bedrock is assumed rigid or fixed, all the waves are trapped in the soil. If rock is assumed elastic, it absorbs some of the seismic waves. Elastic bedrock serves as a radiation damping, where waves partially absorbed do not come back at the soil again, effectively reducing the free surface motion compared to that of the rigid bedrock. This reduces the ground surface response. So let's see if this helps. So assume now waves, we are considering the shear wave velocity and the density of the rock. It's no more rigid. It's no more infinitely stiff. And our soil similar. So for this case, we still have the wave equations, similar wave equation solutions, but now we are considering wave traveling the soil at any depth within the soil at any time t. Our coordinate is right here. The same equation is true for the rock. Now displacement of the wave in the rock, but our coordinate is not the rock level. R is a rock, subscript for the rock. Using S equals to BS for the soil, we know that at the ground surface, shear stress is 0. From there, we know this for the soil. And from ground surface boundary condition, that's why we get it here. But now we can use displacement of soil is equal to displacement of a rock at the displacement boundary condition right here. We're going to use displacement and stress compatibility at every interface. At this point, whatever the rock is moving, the soil is also moving because it's interface point. And shear stress is also the same for soil and rock at this interface point. So there is continuity. So using these relations, stress and displacement compatibility at the interface, and also shear stress zero at the ground surface, then we came up for transfer function following the same procedure. You can see the detail for this derivation in reference 1 section this. So now the transfer function, it has, let me see. Okay, it has this complex damping ratio, impedance ratio, which contains the rock part. So now rock is introduced. It's again, because we introduced damping, the wave numbers, the shear wave velocity, the G, they are in complex numbers. But now the new term here is we introduced complex impedance ratio. When the wave passes from the rock to the soil, now we're capturing it in terms of the rock properties also. It's not only soil properties. So this alpha Z is what's containing the rock part. But this is a form of the equation. This equation remains the same as far as you have, for any soil. H may vary for different soil, input may vary, Vs may vary, but the equation remains the same. So let's see. So we introduce elastic rock now. Rock with some damping. Let me see. We introduce damping in the soil. Yeah, we have damping in both cases, even if I didn't show it here. That damping value is right here. So let's see an example if this helps. We have the rock part, shear velocity in the rock, unit weight of rock, damping in the rock. And soil, shear velocity, unit weight, and damping. The looser a material, the higher the damping, right? So this makes sense. Even this is a stiff soil or dense soil. Sometimes loose soil, you can see it 50%. Rock, you can go to up to 5%, like concrete, things like that. So the stiffer the material, the lower the damping. Repeat example 7.2. This example is still from reference 1, the Kramer book. I forgot somehow to reference 1, to write it here. Repeat example 7.2, assuming that the bedrock is not rigid. Assume a shear wave velocity of 5,000 feet per second, a unit weight of 160 pound per foot cube, and 2% damping for bedrock at the gallery number 1 site. These units are in the US units, that's what we use. In Ethiopia, it's metric units, right? So don't be confused with the foot and pound units. So let's see how it looks like. Now, this is not something you do it by hand. It's more complex because you have to change the time history into a fast, and you have rock motion, transfer function, and then go up. So the same example, up to here, they're the same. The input is the same. The fast is the same in frequency domain, but now the transfer function changed, right? Why the transfer function change? We had it up to 12 earlier. Now it gets lower. Why? Taddesen. Yes, exactly. Because we are introducing elastic rock. The rock is helping us a radiation absorber, radiation damper. See, if the transfer function gets lower, our estimation for the ground surface motion is also to get lower. So you can do the same exercise. Multiply transfer function C by D to get the Fourier amplitude at the ground surface, convert it to a time history, then you get this value. So this is, see this? This is lower than, this is 0.339 compared to 0.45 to earlier. It was much higher. So by considering more realistic case, the PGA estimated 0.339 G reduced PGA compared to PGA of 0.452 G for rigid rock. So by improving our assumption, we are getting very close to what was recorded at the ground surface. At the ground surface, they recorded 0.322 G, but we're getting close, 0.339 G. It's not that bad. There are still some minor differences, but that can be attributed to soil properties and things like that. And also, we are assuming a uniform soil. The soil may not be uniform, and maybe some stratification. Because of all that, you can have minor change. But the big takeaway is when you consider elastic rock, when you introduce the damping part, radiation damping part from the rock, then our estimation is getting much better. So what they recorded in the field is matching what we are getting through this analysis. So you can trust your analysis. It's like kind of calibration, right? So, but in reality, case number 4. Case number 4 is the same to the case 3, except now we are introducing so many layers. Instead of assuming one single layer for the soil, we are assuming different soils because 500 foot, that's like around maybe 150-meter depth, right? It's hard to expect the same constant soil. Even with depths, G increases downward generally. And you may have a sand layer topping, clay and things like that, or limestone in between. So depending on, this is just an extension of the case 3 with different layers, with so many multiple layers. And each layer, even the rock, is elastic, some damping, and damping is not zero in this case. So this is the most general case. So we have the same wave equation solutions. It's the same equation, but now what we are going to do? We are going to do those stress and displacement compatibility at so many points, right? At every interface. At the surface, at the interface 1, interface 2, interface 3, interface N. So it's a lot for hand calculation, right? If you have 100 layers, you can imagine. This is not something you do by hand. But I'm trying to give you, to understand it, how it is done in softwares. So when you run a software, this is what it do, something like shake, a wave propagation. Because they are solving the wave propagation equation, and you can introduce so many layers for shake, and it solves it pretty quick. But this is what it does. So the wave equations for shear stress and displacement compatibility, solution requires displacement and stress compatibility at all interface layers. See detail in chapter 7 in reference 1, the Kramer book. From displacement and stress compatibility at each interface layer, a set of equations are developed to solve for constants A and B at each layer. The transfer function for each layer is solved and used to propagate the motion from the bedrock to ground surface. The solution of these equations is complicated and impossible to do by hand and requires computer programs. So the good news is we have computers to solve it for us. But we are expected to understand what they are doing. Commonly available programs for 1D ground response analysis, you may have heard SHAKE. It was initially developed in 1972. Then Kramer also, our reference book, reference 1, the author of reference 1, he developed something called ProShake. ProShake formerly called, it used to be called EduShake when I was a student. We used EduShake to do wave propagation in the soil. And it used to be free. Now I think it changed. The last time I checked it was last year. It changed their name to ProShake. ProShake is like, I think the commercial version of Shake. ProShake has a student version freely available but with limited capability. 17 max soil layers. You can do hundreds of soil layers if you buy the software. But for students to get familiar, Kramer still made it free thanks to him. Thanks to him, and you can use at least 17 layers. So you can go to this website and download it. www.proshake.com. And another famous software is also Deep Soil. Ashash University of Illinois in Chicago. It's free license for students available, complete version, and this is a website. I'll give you one project on this. You can use any of them. Maybe ProShake is the simpler for you, but you can also Deep Soil if you prefer. So far, we discussed ground response analysis or transfer functions using linear soil properties. What does mean linear? النموذج constant G, constant shear modulus, constant damping. Advantage to linear approach, it's fast, it's direct solution, it's good for very stiff soil, rock, and or very small ground motion. Transfer function can go both ways, up or down. If you have the one at the ground, you just divide it to get the bedrock. If you have the input at the bedrock, multiply it by transfer function, get it at the ground surface. The big disadvantage to linear approach does not account for soil nonlinearity. So still we have some limitation. So when you do the transfer function, you can do it upward or downward. We call it convolution when we go up, and we call it deconvolution when we go down. Convolution upward, you have input at the bedrock and input right here, and you go upward and try to estimate the ground surface. The name is convolution. There are some steps. Deconvolution analysis, there are more details to do it. I'm just introducing you. If you have input motion at the top and try to estimate at the bedrock, that step is called deconvolution analysis. So don't get confused with convolution and deconvolution approaches. Deconvolution, when you go down, starts with the surface ground motion and divide it by the transfer function to obtain the bedrock ground motion. If you have the phase or the time history converted into phase at the ground surface, you divide it by the transfer function, same transfer function, and you get it at the ground motion at the bedrock level. Pretty easy to understand. Linear assumption neglects the nonlinear dynamic behavior of the soil. There are two methods employed today to account for soil nonlinearity. So even if we improve it so far, the whole transfer function approach is linear after all. It's using constant values like a static analysis. That's why it's quicker. But nowadays, to account for soil nonlinearity, there are two ways to do it. I have been repeatedly telling you this one, the equivalent linear approach. At every step, still it's linear, but it varies the G value, the damp value it considers with cyclic shear strain. As shear strain increases, the input that we use for damping shear modulus or shear wave velocity, it changes. So these are you familiar with this? Who can tell me this? Getu. How do we get this GG max and damping curves? Which chapter we discuss we can get this from? The dynamic soil properties, chapter 5. That's an output from there. Traxial tests, resonant column tests, wave propagation tests. If we combine the results from there for different shear strain level, we can get a complete picture for that soil at different strain. So strain compatible properties are what we use to model equivalent linear approach. So the Shake software, if you use it, this is directly an input. We use strain compatible G and damping for soil, and as strain changes, the corresponding values change. The methodology is similar to linear method, but strain compatible properties are used. Methodology is similar at every step for a single step, but at every step we're changing the values as strain increases. The other approach is nonlinear approach. That's where you use constitutive models. They are trying to model at every instant that high stress loop, like the fin model I mentioned. But that's usually done in time domain, and they integrate the equations at every step, and they use very small delta t, something like 10 raised minus 4, minus 5, minus 6, and it's what's implemented like in a finite element, finite difference analysis in Plaxis and FLAC. And it has its own advantage, but it has also its own limitation. It takes a lot of time. It's very time taking, computationally very expensive. But the approach, those approaches, they model also pore water pressure increase. If you do a dynamic analysis and predict also pore water pressure increase at the same time, which means you can model something phenomena like liquefaction. So that's the advantage. Plaxis and FLAC, they can model liquefaction. But the simulation takes a lot of time. But they use constitutive models for that. So two approaches to account for nonlinearity of soil, equivalent linear approach. This is much faster. The speed is helpful because especially if you're doing SSI, if you are modeling the entire structure above ground and so much underneath for the soil, you can do it quickly. It will be too difficult for FLAC and Plaxis to do that. There is limitation. So FLAC and Plaxis right now, it's like they are good for research purpose. You can model liquefaction, things like that. For application for industries, for SSI, it's limited. And nowadays we have supercomputers to do that, but if you are using supercomputers, you may be able to solve a big problem. So that's the limitations and advantages with these two approaches. So comparison of equivalent linear and nonlinear approach for ground response analysis. Equivalent linear approach, this is like shake. These are the ones using degradation curves. This is the one using constitutive models. So equivalent linear approach, it's frequency domain, the solution. The fast we talked, that's in frequency domain. So you can solve it for selected frequencies and combine results at the end. Nonlinear approaches, it's time domain, direct integration of like a wave equation at small time step, 10 raised minus 6. You pick some delta t, solve it, all those finite elements, then you pick another delta t. It's very time taking. You go step by step. Solution usually requires only at selected significant frequencies, and interpolation can be used for other frequencies. That's in frequency domain. That's why it's quicker also. But nonlinear approach is something in FLAC and Plaxis. They require solution at all time steps. You go from 0 to 30 seconds in the time history, if it is a 30-second duration. And that is 10 raised minus 6. All those calculations is very time taking. Equivalent linear approach, strain compatible properties, G and damping are easily available from lab or from field test. You can get these values from field test from lab. That's why nowadays this is done in the lab and it's an input to the equivalent linear approach. But the linear approach, they are reliable on constitutive models for complex soil response. High stresses loop at all strain levels may be challenging. There are some models developed, tested. They are very promising, but it's hard to get for all soil types. As the soil changes, as the depth changes, it gets more complicated. So there is some limitation. So this is more of a research than ready. Right now, I don't think it's ready yet for the commercial application or for designing. It can provide a good result in combination, because there is some limitation in both of them. If you do both, they can complement each other and you get the best out of the two of them. Equivalent linear approach cannot model pore water pressure increase, hence cannot model liquefaction. For this case, what we have been doing, even myself, is we do equivalent linear analysis for the stress part. We use it for design. Then for the liquefaction, we use the factor of safety evaluation we studied yesterday. We implement that in Excel and MathCAD, and from the field tests, we try to get those factor of safety and check if the soil is going to liquefy or not. If it doesn't liquefy, then our analysis is good. If it is liquefy, what do? We do some kind of mitigation. So this has to be, this equivalent linear approach, it has to be combined with other techniques to evaluate liquefaction. But with the nonlinear approach, those cognitive models, they can model pore water pressure increase using cognitive models, and hence can model liquefaction. Equivalent linear approach, widely used for practical application. I've been using this technique for nuclear power plant design. We don't even use nonlinear approach like FLAC and PLAX because it's limited. Section 9.2, introduction, soil structure interaction, SSI analysis. Let's cover this after a break, coffee break.